So today we finish our discussion of the regression with panel data. Let us first remember what we did last time. The most important problem that we always discuss, and we are looking for potential tools how to overcome this problem, is the omitted variable bias. So this is the common problem if you want to know the estimate of a quantitative effect or if you want to quantify the causal effect when you make some action and you want to predict what is going to be the outcome of this action. So omitted variable bias can make this estimation wrong. And last lecture we introduced the approach using panel data that if some factors are not observable, not measurable, or even if you don't know them, but panel data can help you to alleviate this problem. In the case of what? In the case when these unobservable factors are not changing over time, but they are different to different entities. So we showed this ability of the panel data using the example of Irkutsk effect on traffic death rate. So we did separately cross-section OLS regression for 1982, then for 1988, and the surprising effect was that the result, the estimate, was positive. And kind of we stated that this positive correlation between beer tax and traffic death might be because of the omitted variable bias. So this is not a true causal effect. This is far away from the expected value of the causal effect. Why? Because, well, we believe that there is omitted variable bias. Once we regress the difference in fatality rate on the difference in beer taxes, we estimated something reasonable. The effect was negative, it was statistically significant, and we believe that at least we are closer to the estimate of the true causal effect. Please remember that we never know about the true causal effect, and we never know about whether we controlled for all factors. I was trying to give you this idea throughout the first part of the course, throughout the Econometrics I, and please keep in mind this idea. You never know if this is true, if your estimate is close to the true causal effect or not. The only way to do this is randomized control experiments, but if you are using the observational data, it's not always possible. So the question that is left after the last part of this topic was, what if we have more than 2 time periods? What if we have data for 7 years as we have here? Is this possible to leverage on it somehow? So before we start, are there any questions regarding the previous part?
I have no.
Let's move on. Well, so now we introduce model which is called fixed effect regression, and this model helps us to use all the available data over several periods of time. So the first question we posed is, what if we have more than 2 time periods? So consider this model. It must be familiar from the last lecture. We have an outcome variable. We have an intercept. Look, this intercept is constant. It does not change over time. It doesn't change over entities. It's just constant. We have slope, which is the same for all entities and across all time periods. And we have this variable z, which is unobservable, but which is constant over time, but differs across entities. Yes, so z varies from one stage to the next, but is constant over time. We can define, this is just a formal mathematical step, we can define a variable alpha I, which is going to be different for different entities, i's, as beta 0 plus this term, beta 2 times zi. Well, in principle, nothing is wrong here, and then we can rewrite our model in the following way. So what do we have here? We have a slope, and this slope is the same for all entities and across all entities and for all time periods. And we have intercept, but now intercept is different. This intercept differs for different entities. Right? So this regression model with n intercepts. Each intercept for every state or for every entity. Last semester, we had something similar. Does anybody remember when we had different intercepts but the same slope?
Can you give a hint?
Yes,
Well,
please.
just think about this. Your intercept, so the level of y when x is 0, is different for different groups.
Maybe
Do you
with dummy
remember?
variables?
Yes, we introduced this idea already when we spoke about dummy variables. We took two different groups, we introduced dummy, and this dummy worked as the different intercept. So you see that the idea here is very similar, but now instead of a dummy variable, we have just intercept for n different groups, which are entities in our case. And this equation is called the fixed effects regression model. So this is the usual name for such model. When you have one slope for all entities and over all time periods, and you have n intercepts, so different intercept for different entity. These alpha 1 to alpha n are unknown intercepts, and they must be estimated, one for each state. So it's just an extension of what we know from the dummy variable. And we call them entity fixed effects. So why fixed? Because they are not changing over time, and they are fixed for every entity. But those are not those entity fixed effects are not interested to us. So we are interested in beta 1 as usual. So this is just a kind of the byproduct of this estimation. So let's try to understand what are these fixed effects and how to interpret them. Suppose we have three different states: California, Texas, Massachusetts. And from that model, from the fixed effect regression model, we will have three different intercepts for every entity, like here. So we have the same slope for a regression line, but every entity has its own intercept. If we have kind of 40 entities, we will have 40 lines with the same slope and with a different intercept. And since this is very similar to dummy variables, we are able to model the same thing with the help of binary regressors. We just need to be inventive a little bit. So let's define a dummy variable which equals 1 if there is the entity number 2 and 0 otherwise. Let's define D3 equals 1 when there is a third entity and 0 otherwise, and so on. If we have 48 entities in our data set, we will have 47 dummy variables. So n minus 1, because for the first entity we do not introduce a dummy variable. And in this case, the model becomes this model. Look, we have 1, 2, 3, blah, 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 n minus 1 dummy variables for every particular entity. And intercept. This intercept is going to be the intercept for the first state or for the first entity, right? Because if all dummies are 0, then we are talking about I equals 1. So this is the entity number 1. So these two models, so the model from the first slide, entity fixed effects model, and this one are totally equivalent. And you will derive the relationship between these two models on the exercise session. So it's very simple. If you just think about this, you will be able to show what is alpha 1 from this model, what is alpha 2 from this model, and so on. So how they are related to the dummy variables representation. Okay, so let's see what is the result of this estimation. So once we estimate beta 1 using entity fixed effects, we have the following result. If I remember correct, when we used only 2 time periods, 82 and 88, the estimate was something like minus 1.04, something like this, minus 1. So now the estimate is smaller, but statistically significant. So the effect is less strong, but it's still statistically significant. And what is the most important, it's again reasonable, it's negative. So if I change BRICS by $1, so fatality rate drops by 0.66 people per 10,000, right? So it was in 10,000s. And usually we don't report all those dummies. So just imagine we have 47 intercepts. For 47 intercepts, those are not of our interest. We just don't report them, because otherwise you will have a huge table with a lot of the information there, and that information is not that interesting for us. That's why in this table we have only this. But if you want, on the exercise session, you will see how to extract those state or entity fixed effects from this model. It's very simple. Now, we try to develop this model slightly. And what if an omitted variable is different over time, but is the same across entities? So can you give me an example in this particular case when we are talking about beer taxes and fatality rate? What might be a variable which is the same across all states, but which differs over time?
Some laws, maybe legislations.
Okay, maybe some legislation which is the same for all states. I agree. It might be changing. What else? Well, okay, there might be some technical progress, and there is a safety. So there is a car safety. Over 7 years, the safety of cars might be improved, and this is another case why we can observe a reduction in a death rate. So maybe this is just a coincidence that over time we observe a reduction in, increase in beer taxes and reduction in the mortality rate, because, well, maybe this reduction is attributed to the safer cars, better quality of cars, better quality of roads, but not to the beer taxes itself. So this is also another unobservable effect, which we believe changes over time, but it somehow influences all states simultaneously. And this, extending the idea from the previous slide, this produces intercepts that change over time. So now, for each state, we can observe change in intercept over time. And let's just denote these changes by another variable as t. So look, now this variable changes over time, but is the same across entities. And then the regression is going to look like this. So we have the variable of interest here, xit. So we have the common slope. We have one variable which is constant over time but different across entities, and we have another variable that changes over time but is constant across entities. Following the same logic, we can represent this model in the following way. So we have entity fixed effects, alpha I, and we also have time fixed effects, lambda t. And this model is called the entity and time fixed effects regression model. Or sometimes people call this two-way fixed effects. So two-way means that we have one way in entity, another way is time fixed effects. So two-way fixed effects. These terms lambda 1 to lambda t are called time fixed effects. Again, we can introduce binary variables for every time period but the first one. So we introduce a dummy variable for second time period, b2t, which is equal 1 if there is a second time period and 0 otherwise. b3, then b4, b5, and so on. And as a result, we have this entity and time fixed effects model with a lot of binary or dummy variables. We have a variable of interest here, and then the rest is just a huge line of binary variables. So in our case, in the case of beer tax and fatality rate, let's count. We have 48 states, minus 1 is 47. We have 7 years, minus 1 is 6. So 47 plus 6 gives us 53 dummy variables here. Again, we will look into the relationship between dummy variables representation and fixed effect representation on the exercise session. This is very simple, just 1 or 2 steps to show how this B2, delta 2 B2 is related to that lambda t, depending on t. So once we estimate this model again, this model is estimated with the help of OLS. Once we know all these dummy variables and things, it is in principle possible to estimate this with OLS. Well, yes, we have now the estimator, which is called panel OLS here, the result from Python estimation. But basically nothing prevents us from using the familiar methods of OLS estimation. And look, the parameter here, the parameter estimate is quite close to the entity effects estimator. So that time it was minus 0.66, now it's minus 0.64. Well, significance slightly decreases. So it was p-value of 2% initially, now it's p-value almost 5%. We are on the border between rejecting null hypothesis and not rejecting null hypothesis. But okay, so let's take it as statistically significant, estimate minus 0.64. So we still see that there is an effect of a beer tax on the fatality rate. Smaller, but still significant. So here is the result. What do we see? As I said, in this specification, we included beer tax as a variable of interest, 47 binary variables for states, for entities, 6 binary variables for time. So overall we have 47 plus 6, it's 53, plus beer tax 54, plus constant 55, so 55 right-hand side variables. So constant is not reported here, but it's somewhere there when we estimate it. So 55 right-hand side variables. Of course, the dimension is huge, and we are not talking about the technicalities of this estimation. As I said, OLS in principle is applicable here. You just stack all the observations with all these dummy variables and regress y on 55 variables and you are fine. The problem is that there are a lot of variables, and well, sometimes the computational power is not enough to estimate it. If you want, you can read some books on panel data, regressions, and you can look how people overcome these problems. They usually do some tricks, mathematical tricks, how to reduce the dimensionality of the data and how to make this regression simpler, keeping the estimated result unbiased and keeping the estimated result same as here. We are not talking about this. It is not my goal to give you all this mathematics behind the estimation, don't worry. So for us it's gonna be totally fine if you know how to press a button, write necessary code in Python and get the result as I showed you on the previous slide. That's gonna be totally fine for you, and you need to be able to interpret the result. Well, we have this result. It means that the effect of x on y is significant, not significant, positive, negative. Practically, it means the following. So that's all. For me, it would be enough. So we don't report, as I said, time and state binary variables and their estimates. Those are not interesting for us. And well, we know that this coefficient is significant at the 5% level, and we hope, okay, no, let me say it differently. We know for sure that this estimate is immune, so is not affected by the omitted variables that are constant over time or constant across states. This is an important thing. because it is still a possibility that we omitted some variables that are not here. Those variables, omitted variables that are changing over time and across states. So we killed some unobservable factors. Yes, this is okay for us. But still, there is a possibility that some factors are not counted here. Those factors that are changing over time and across states. So it's still possible. Don't believe this result. Don't think that this result is the final correct result, and we can say, well, increase in beer tax by $1 reduces the fatality rate by 0.64 per 10,000 people. No. It is still possible that we forgot about something. Your home assignment. So I will talk about it later, but your home assignment is going to be to read this section 10.6 from the book. This one, where authors report regressions, entity and time fixed effects regressions, including other control variables, which are changing over time and are different across states. So please consider this before you make your home assignment, just to see how the effect changes. So you see that this effect basically becomes not significant once you control for other important variables, which probably suggests that beer tax does not have an effect on the fatality rate, right? So look at this closer and try to understand what is going to be the change. What is going to be the change in the estimated result once you control for other omitted variables. Questions here?
So what, I didn't see what are the factors. So it supposes, it suggests that if we add the factor that changes, that is not constant over time and across the states, then beer tax is not significant.
Well, we cannot claim this before we make an estimation. But here, once you read this chapter, you will see. Then, for example, once they control for such variables as, these are dummy variables, drinking age, 18, 19, 20. Or they control for the drinking age as not as a dummy variable, but as the continuous variable. There is also there are some variables that control for the legislation which changes over time and which is different across states, because there is also some state level legislation which also changes. So mandatory jail. So there is some variable controlling for the average distance that driver passes every year. Unemployment rate, which might also sometimes, this is an economic factor that controls for the social, let's say, welfare, and so on. So just try to look at this and try to understand why every variable is there and what happens to the estimate of the effect, and the estimate becomes not significant. Yes.
Okay, I see.
Yes, so I guess for you it's gonna be not that difficult task. Just read, try to understand what happens, and then you will answer several questions in your home assignment. So what we need to discuss here, some technical things. You probably have noticed here that there is test for poolability. So this is a new thing which appears here compared to the previous estimations when we used OLS, because all the other things are here more or less familiar to you. There are some the number of entities, the number of time periods. Yeah, sorry, we have basically it is confused somehow because it must be time periods 48 and entities 7, but it doesn't matter. So the estimate is going to be still the same. Yeah, so F value, which is just a test that overall regression model is not significant. And this one is the new thing, which is a special thing only for the panel data regression. So let's talk about it a little bit. So basically the question is, are these fixed effects present in the data? So we are using all these things, but the question is, this is our suggestion that there are unobservable factors constant over time, but different across entities, present in the data. Maybe not. We don't know. This is our suggestion. And we want to test this. If we, for example, estimate such model, so this is beta 0 in our previous regression, this is beta 1. I just changed this to alpha and beta. So look, alpha is constant across entities, across time. So no index here. This is beta 0. This is beta 1. So our null hypothesis is that the true model looks like this. No fixed effects at all. Our alternative model is that alpha changes over time, like this, alpha I. So we want to test if these fixed effects are there. Are these fixed effects there? Yeah, so we test for the presence of individual effects. And another way to formulate this null hypothesis is that alpha i's are 0 for all i's from 1 to n. So no alpha I is there. And you see that that test is called F-test. So you can, I guess, you can suggest what statistic is used to test this hypothesis. Another, if you want to test for the presence of both entity and time fixed effects, our alternative is going to be like this. So the null hypothesis is still the same. So we have one intercept for all entities and for all time periods. An alternative is that we have different intercepts across entities and different entities for time periods. So in our example, we have this F-test. This is the model with time and entity fixed effects. We have F statistic, we have p-value, we have the distribution for this statistic, and well, what we can conclude considering this, which hypothesis is rejected.
We cannot reject. Oh, wait. We can reject null.
We can reject the null hypothesis, which means practically what?
That there are effects, fixed effects.
There are entity and there are time fixed effects. So if we go back, I didn't report it, but if you go back to the entity effects only, we see that entity effects only are also present here, right? So p-value is very small, close to 0, and f-value is large. So entity effects are there. We believe that there are some variables, unobservable variables, that are constant over time and different across entities. And once we introduce time effects, those are also here. Yeah, the test rejects the null hypothesis, and both entity and time effects are present. So now, the last thing in this topic we need to discuss is about standard errors. So I hope you remember that we spoke a lot about standard errors in our first course in econometrics. Why this is important? Once we make hypothesis tests, the significance of estimates depends on our estimates of standard errors. So basically, standard errors do not influence the estimate of a coefficient. We don't care. But once we want to test the significance of this estimate, the way how standard errors behave can influence our inference about these estimates. So this is important thing. So we need to understand if there is something special about standard errors when we estimate panel data regression. So first of all, let's try to discuss the assumptions. The assumptions are always important to understand where exactly you can have a problem. So the first assumption is the same as for the usual multiple linear regression model. So UIT, now with the time dimension, has conditional zero mean. So conditional independence. Once we control for all axes across time and for entity fixed effects, this is zero. Look, xi means the observation of x, in the first time period, in the second time period, blah blah blah, until the t times period, so across time. Once we control for x's and once we control for these fixed effects, the conditional mean of the error term is zero. Look, these observations together with the errors, again across time, over time, they are independently and identically distributed. So which means that for every state, the distribution of these things must be similar. But it, in principle, it can be different over time. So number 3 is, as usual, large outliers are unlikely. And number 4, that there is no perfect multicollinearity. So I hope you remember, we do not include variables that are correlated or highly correlated with each other. We usually prefer that variables included in the model are somehow as low as possible correlation. So assumption number 2 for panel data holds that the variables are independent across entities, right? But it doesn't make any restriction within an entity. So it doesn't say that for the entity, for the same entity, for the same state, for the same person, for the same firm, the observations must be independent over time. And this is reasonable. Just try to think about it. If you take a particular state and if you observe there the level of a beer tax over 7 years, you cannot say that once you know about the level of a beer tax in 1982, then the level of a beer tax in 1983 is going to be independent of it. It is not possible. Once we are talking about time dimension, we'll talk about this more once we introduce the time series econometrics. But for now, try to understand. If I know that in the particular state, a beer tax was, let's say, $3 this year, can I say that next year it can be any number from minus infinity to plus infinity? Well, probably no. Probably I can say that if now it's $3, then the next year is going to be close to $3. Maybe slightly more, maybe slightly less, but it's highly unlikely that it's going to be like 10 or 15 or 0.1. It is more likely that the level of x is going to sustain close to the previous time period. And if I take another state where the level of a beer tax is, let's say, $0.5, 50 cents per case of beer, then the next year I cannot say that it is likely that it is going to be 3. No, I can say that it's likely that it's going to be very close to 0.5. And we saw this in the data. You saw that, let me show you. It must be here. Yeah, you saw that, let's make it larger. Oops, no, not like this. Yeah, look, once we observe the first state, the level of a beer tax is close to some level like 1.5, let's say. Once we take another state here, the level of a beer tax is different, and it is not kind of fluctuating across the same center as here. So here the center, the mean is something like 1.5, 1.6 probably. Here we have something like 0.3 maybe. Once we take the third state, that level is gonna be also different. Where is the state number 5? Yeah, look, beer tax here is 0.65, 0.67, and so on. So this is the meaning of the second assumption. Look, that the observations of an x variable for state I and the whole stream of these observations over time in the first year, second year, third year, and so on, this group, this series of x's must be independent from another state, but they are not independent within the state over time. They are not independent. And I hope you see this. They are related somehow to each other. You cannot claim that a variable can be independent over time. It's something like, just think about your future salary. If your salary over time is going to be independent, it means that every month your employer is going to, I don't know, randomly decide what's gonna be your salary. today your salary is 0. Next month your salary is 1 million rubles. Next month your salary is 10,000 rubles, and so on. I hope you understand that in practice it doesn't happen. If you somehow agreed on your salary is going to be not constant probably, but is going to somehow connected to some value, and you cannot say that, well, next month my salary is completely unpredictable. No, you have some anchor. You have a value of salary this month, and with the help of it you can predict what's going to be your next month's salary. The same stuff here. I hope you understand this idea that variables are not independent over time, but those are independent across entities.
It is clear you have already described everything, maybe on the previous class.
No. Wait,
series.
I'm
No?
talking about slightly different things right now. It has nothing to do with the previous one.
Okay.
Okay, so yeah, X can be correlated over time within an entity. That's what I was talking about right now. So your salary is correlated with itself, basically. Like, and there is an important concept which we are gonna explore during the time series econometrics part. Well, if we say that xit is correlated with xis, look, what is s? S is just some different time period. So this is the first year, this is the third year, let's say. So for different values of s and t, or we can say also, there is another term, if xit is correlated over time for a given entity. That was my example about salary, about taxes, that they are not changing like completely independently. They are somehow tied to the some common level. We can say that xit is autocorrelated. So autocorrelation is an important concept in time series. But we also need to introduce it here because, well, we still have this time dimension. So all correlated with itself at different dates. Or another term is serially correlated. So all of these things are interchangeable. You can say correlated over time, you can say autocorrelated, you can say serially correlated. No difference. Everybody will understand you. Then there is a problem. Because look, we used OLS to estimate this model, but we cannot use heteroskedasticity robust standard errors because now this individual observations are correlated with each other, and this is a problem. We need to introduce a new estimator for standard errors. Again, I avoid a discussion of mathematics behind it. You just need to understand why we are doing this, what is the source of this problem, and you need to understand how to solve this problem with the help of Python. That's all. So that was my introduction. So the single hypothesis testing depends on the values of the standard errors, and standard errors must be correctly estimated. So we need to use a correct estimator. So last semester we spoke about heteroskedasticity as a potential problem, and we introduced heteroskedasticity robust standard errors. So different estimators that are able to capture this problem. Now we have another problem. Yeah, so For the cross-sectional data, we use this heteroscedasticity robust standard error size HT0, HT1, common in Python. So now, together with this heteroscedasticity, we have another problem, which is autocorrelation of the errors. And standard errors, once you use this HT0, HT1, are not gonna be correctly estimated. So those are not valid. So we need to introduce something which is called heteroscedasticity and autocorrelation consistent standard errors. Or shortly, they are called HAC, standard errors. So if you have a time dimension, so kind of in short, all my long words short. If you have a time dimension, you must be careful with the fact that over time your variables can be correlated with itself, can show this autocorrelation. We will talk about autocorrelation more in details during time series econometrics, but right now I hope you understand what does this mean. It means that every other year your value somehow depends on the previous value. Then you need to apply a special type of standard error estimators, which are these HAC estimators. And there are a lot of types of these HAC standard errors, and one of them is clustered standard errors proposed by Stock and Watson in their book to use in panel data. So in a nutshell, once you do the estimation in Python, don't forget to write instead of HT0 or HT1 this type of the variance covariance matrix. It must be clustered now. Why clustered? Because we have a cluster of one entity which contains several time periods. That is why we call them clustered. Yeah, okay, so, and what else we need to take into account here, that once you include entity effects and once you make an estimation in Python, you need to introduce this additional parameter cluster entity equals true and cluster time equals true once you cluster for the time dimension. Well, usually you just control for both, for time and for entity. Just, it doesn't harm if you put both truths there. You will revise the code and you will see how this works. No difficulty here, I hope. Questions here?
No.
Same on my side.
Nice. Well, let's conclude. What do we know after these two lectures? First of all, it is always good when you apply, when you collect the data over time for different entities, because in this case you can use this rich data to control for unobserved emitted variables. The assumption about those emitted variables is that they do not change over time if we introduce entity fixed effects, or they do not change, they do not change over time, but different across entities, or they change over time, but they are the same to all entities. So entity fixed effects and time fixed effects, respectively. As we concluded several slides ago, those are not universal, and those fixed and entity the entity and time fixed effects are not able to control for omitted variables that vary both across entities and over time. Like some economic factors we have seen from the book, or some other variables that can potentially be correlated with X and can influence on Y. So remember these two conditions when the omitted variable bias appears. So regression with panel data is not able to eliminate the influence of these factors. It helps us to some extent, but we still need to keep looking for the better tools to solve this problem. So we'll be doing this in the next lectures, as you can guess. Your home assignment for the upcoming week. Please read section 10.6 from Stock and Watson book for the empirical investigation of the effect of beer tax on fatalities. So this is optional, but I strongly recommend you to do the self-study on the panel data regression. It is here. Yeah, self-study number 1. You have a solution, so the code is available with the solution. You can look there, and it will help you, as we discussed the first lecture. It will help you first to solve your problems with Python, to receive higher grade than just satisfactory grade. So don't ignore, please, this. It is designed to help you. So there is a quiz number 2 after lectures 2 and 3, so panel data, and also you will have some questions from related to this section 10.6. It is available until Wednesday midnight. Here. Quiz 2, lecture 2, lecture 3 as well. And home assignment number 2. So here you don't need Python, as I promised. You will have a chance to pass this course without Python. So therefore, this quiz does not require Python. You just need to understand the concepts and how to apply them. And here, the estimation of fixed effects regressions with the help of Python until the next Tuesday. So wait till the exercise session. On the exercise session, you will make a revision of all the estimations that I did for lectures. You will reproduce all those results that I showed you on the lectures. And then you, after self-study, you will be fully prepared to pass this home assignment number 2. That's all from my side for today. Was slightly shorter, but I guess it's okay for you.
We don't complain.
I guess so.